we come to a piece of technology that's called DNS, and it's being used implicitly even if we don't explicitly call it from the code. And that's DNS. Let's talk about DNS, Domain Name System. It's a very interesting technology, and I think without it, our life will become very difficult when it comes to networks. Not just because the IP addresses, which is really the only way in the internet, in the network, to address a machine or a process. And that in itself is cumbersome because we humans don't really do well with numbers. We don't really memorize numbers. We do better with names. So we created this concept to essentially create an additional layer of abstraction, which proves very useful because now I can simply provide a name, and that name is all what I need to remember. Example.com. That then points to the IP address where the example.com machine is hosted. And by doing that, we get other things for free, other pieces of useful information. Not only I can provide one machine, but I can provide 10. Why not? And I can do load balancing between them. I can do redundancy. All right. If you ask me what's the IP address of example.com, sometimes I'll give you it. I'll say it's 23.192.228.84. And then another time I'll give you this. Another time I'll give you this. It's different. And these are called A records, which is the IPv4. So that's the usefulness here. We get away from dealing with numbers, but then we abstract it out with the names, and we get load balancing for free. And not only that, you get other beautiful features. You have a repository of stuff you add records to, right? We don't have to only have IP addresses. For this host, give me the mail extension. Where is your email server? For this record, give me the text record. Additional information. For this record, give me the HTTPS server that supports it. And there's like a lot of other records. That's why we didn't have a problem when IPv6 came into a picture. We just added another record and we called it AAAA, literally. Right? That becomes the IPv6 endpoint. So the DNS didn't really change. It's just how we query it changed. So it's very critical. So it points text. It is a text that points to the IP or a collection of IP address. It's an additional layers. It's a great abstraction for this particular change. IP address changes. If the machine goes down, that's fine. You don't have to worry about it because you're no longer pointing to a physical machine. You're pointing to to this domain, and that domain is translating always to the latest IP addresses. Right? And this way, we can do tricks too. We can do geo DNS. If you're in India and you do a DNS or example.com, the client is smart enough to pick the closest IP address that's geo-referenced to India. Right? I don't know where these IP addresses are, but you can find out easily where in the world an IP address is because it's all partitioned. The IP addresses are divided in a way such that they are per location in the world. And I'm glad we did this because now we know that, hey, yes, I got an IP address in America, I got an IP address in the China, and another in India, and I'm from India, so I rather use the IP address in India, right? And then you just connect to it, and that's a client-side logic that does that. Okay? Some smart websites like Google does it even slightly different. I don't know if you, when I was in Bahrain, when I go to google.com, I immediately get redirected to google.com.bh. How does it know that? Because I want to go to google.com. But google.com immediately checks on the server side. So google.com will give me the IP address of one whatever, right? The browser picks an IP address of the DNS. We connect, and then we get back the IP address. Maybe it is in America, maybe it's in Bahrain, maybe it's in anywhere in the world, right? And then we connect, and then we took the hit to connect to a far machine. But then when we came back and we sent our GET request, the web server detected that our source IP is in Bahrain, or is in India, or is in Turkey. And then says, wait a minute, you're coming from Turkey. Why are you coming into America? Right, here is it. Let's redirect you. So we're sending back a header that says, hey, location, go to http.com.bh. If you're coming from Turkey.tk or whatever, right? If you're from India.com.in, I think. And that's it. .com.in always gives you Indian IP addresses. .com.bh always give you, that doesn't necessarily Bahrain IP address, but closer by, like in the Middle East. So probably we're going to get into the one in Dubai, right? Or somewhere closer. So that's the idea. So we are just being clever. DNS, that's what DNS is. So again, so the new addressing system means when we introduce a new addressing system, that means we need a mapping. And that's why we have DNS, right? As a result, we talked about that a little bit. Okay, so here's the thing. I talk about this in my network course, but there's always, every time you introduce a new addressing system, you need some sort of a mapping protocol. Here's an example. When you want to send a frame to an IP address, and I'm talking locally between two machines in the same network, you cannot just send it willy-nilly. You need to know the destination MAC address, the media access control, the actual network card address. That's because that's how layer 2 works. You need that. IP address doesn't give you that information, right? It's a network protocol. It's not a data link protocol. It's not a link protocol directly. So we have ARP for that. Address resolution protocol, which is like if fans out says, hey, who has this IP address, and the one who does gives you back the MAC address, and then you say, oh, now I cache it in my ARP table, and now I can communicate with this direct machine. Same thing on the DNS. If you have a name, you need the IP to connect. You cannot use the name to establish a TCP connection. Just like you couldn't send a layer 2 frame to a machine without knowing the MAC address. You cannot establish a TCP connection without knowing the IP address. And so then the lack of knowledge of the IP address, because we don't want to remember it because it's cumbersome, and introducing this new mapping system, we need the name. And because you need a name, you need a mapping system. And that's why we need DNS. So, there's always a mapping. You'll always find this in software engineering. That always, most of you are like intermediate to advanced people, engineers, and you must have seen this. Like I always like, I don't have this, so I need to map it, and this mapping is stored in one table or another, or hash table, things like that. And DNS is built on. Let me erase this. DNS is built on top of UDP. What the heck does it stand for? I forgot. UDP, datagram protocol, unified, unidirectional, a user datagram protocol. Is TCP built for aliens? Why do we call it user? I think we called it user because it's a user message. Whatever the user message sent is exactly becomes a datagram. In a TCP, that's what I think. In the TCP concept, if you send a message from the application, from the user, it does not become a TCP segment directly. No, it can become one or more. The segments is just a stream of bytes, right? It's translated. So that's why it's called user datagram protocol. Yeah, I always forget that it's called user. U stands for user. And the default is 53. And it has many records, as we talked about. We have A, IPv4, IPv6, MX, I think is the mail. Text is an additional text record, and CNAME, very important. That's for aliasing. Canonical name, right? I use CNAMEs all over my website. Like if you go to my courses, courses.husseinnasser.com is actually a CNAME to another website. So how does DNS work? No? How does it work? So it's a clever design, and I think it was one of the most clever design that we ever did. It's a distributed system, replicated. It's a clever, right? Because think about it, right? Before we look at this, I don't want to shove information at you, you guys. I want you to just think logically about this, right? Because this is not, I just opening your mouth, I give you information. I just think for yourself, how would you build something like that? It's really a mapping system. Name, I get you an IP address. That's just a database, a key value store. So why don't we build something like that? You can. But people thought about this initially. It says, okay, let's just build a key value store. One machine will have every single possible host name. But you see the problem with this one. Internet is massive. And doing that database might be petabytes. It's going to be massive. So what do we do with databases? If you took my database course, what do we do when something is large? The best way to work with 1 billion raw records is to avoid working with 1 billion raw records. That's the best way. There's no other best way. You don't do anything else. There's no magic. We don't force. You go with the river. You go with the flow. You go against it. You don't fight nature. And databases is just nature. The nature of things is it has billions of rows. And you don't say, hey, I'm going to conquer you. I'm going to parallel process this and that. No, you don't do that. You partition it. And that's what DNS did. They partitioned it. So how did they partition it? They said, all right, how about we do this? We're going to build the URL in such a way that it's example a dot com. The URLs are broken in such a way that there's always this top level domain. And it's called .com, .org, .net, .bh, .ein, .gov. They built it purposely this way. And then the other name is just the other name. So what they did is like, all right, we're going to put all the hosts for .com in one bucket. The TLD, the top level domains, tells us the IP addresses of these .com domains, right? So if we want to search for anything .com, you go to this particular top level domain, and it will tell us the list of hosts that end in .com. If it's org, we look at something else. And then we had this problem. Now, of course, that .com is massive enough that everything becomes .com, that even that you need a little bit more partitioning. So if you go to the top level domain and ask for example.com, you're not going to get the answer. No, it doesn't work like that. They broke it even further. Added something called authoritative name server. This is an IP address of the name server that knows the actual IP address. All right. And then you query the authoritative name server to actually find the IP address of the actual machine. Okay. And then you might say, how do I find this TLDs? You need another layer, which is the root servers, right? That tells us it hosts the IP address of the TLDs or the top level domains. So you see, it goes like this. Root gives us the top level domains, right? If you query the root, you will tell us an IP address, because this TLD, there could be a .com TLD and .org TLD, a .net TLD. Yeah? But a .com TLD might be, I don't know, 100 .com TLDs. Which one do you want? Again, those even that is load balanced, right? So you query the root, it tells you all the .com TLDs, and you pick one. Maybe it will give you one, and then you query that, and .com says, okay, what are you interested in? Well, I'm interested in example.com. So it will tell you not the IP address of example.com itself as a website, but no, it will tell you the authoritative name server, the host, the registrar, if you will, of who registered example.com and who owns it. So that's another IP address that you can connect to and ask the question, what is example.com? And it will tell you the IP address of example.com, and you can connect to it. So let's go through an example. How do we actually do this? All right, so let's go through an example of how DNS works. So this process, the DNS works with the logic is contained in something called the DNS resolver. And the resolver does the logic that we talked about. So how does it work? It caches. It's really nothing but a front-end application that does that. And it's also a back-end because we connect to it and ask it that question. But it also acts like a front-end to do all of this work. So how does it work? So there is this root server, which hosts all the IPs of the TLDs. Then there's the top-level domain server, which hosts all the IPs of the authoritative name servers. And then there's the authoritative name servers that host all the IPs of the actual target server. And this is what we want. But in order to actually satisfy that, we do this. An example, I want to go to google.com. And this is the google.com server. And this is the IP address, 142.251.40 and 46. And I don't know this yet. As a client, I ask my resolver. So this indicates that you know your resolver. What is an example of a DNS resolver? 1.1.1.1. Another example, 8.8.8.8. That's Google's. 1.1 is the Cloudflare. Another example is your ISP can act like a DNS resolver, right? Your router can act like a DNS resolver, and that's basically the default. When you connect to your network, you can actually see who's your DNS resolver. It literally says DNS. Who's your DNS server? Who should I send DNS queries to? And you need to know that. And you get this knowledge after you do a DHCP with your router, and you get your IP address, and you get, hey, here's your gateway, here's your IP address, here's your default gateway. If you don't know where you're going, send it to me. I'll take care of it, like a proxy, if you will think about it. And then here is your DNS server for your DNS query. And then you send the query, says, what is the IP address for google.com? And you ask the resolver. The resolver will check its cache. And if there is a cache entry for google.com, it will reply back. Let's assume there isn't, of course. So it will ask this question. It will break this. It will do a string comparison, .com. I'll take the .com, and I need to find a .com server TLD. So that's the second question. Who does it ask? It asks the root. How does it know the IP address of the root? This is well known. There are around, last time I checked, it was like 13 servers around the world, but they are themselves replicated. And then you just funnel through these servers. No? And they're replicated around the world. A list of root servers. And these are well defined. So you connect. And you say, hey, give me a .com server, because I don't want to hard code the TLDs. Right? You ask the root, and it will tell you the TLDs, because these guys change all the time. All right, I got a server, TLD1. Assume this is an IP address, right? So you get an IP address of a TLD1 server, top level domain that is a .com domain. What do you do this? Now you ask a second question as a resolver. I'm trying to get to google.com. Who owns this? What authoritative name server actually has this? And you get back a name address. An IP address that's called ANS1. Assume this is an IP address, right? An actual IP address. And then you turn around and connect to that. Remember the outage that happened to Microsoft during the pandemic? It happened right here. Because the authoritative name server of all of Microsoft just went down. So this step worked. this step worked, but this step failed because it couldn't get the Google IP, the Google.com IP, because this guy was not reachable. Because these machines disappeared from the face of the internet. And I think the same thing happened to Facebook. That's why people say it's always DNS, right? Because of this reason, because there's always like a single point of failure. And this is it for people. Google.com is alive and well, but we couldn't answer the question of who owns, what's the IP address of Google.com. If you understand the question, right? I know Google.com is alive. There is this IP address, but you don't know it. If you know it, you can connect to it directly. But to ask the question, you are being rejected, because if the authoritative server is down, then you cannot get that answer. But let's assume everything is hunky-dory, and we get the IP address, and then we cache it, and then we reply back. And that's how DNS resolving works. The next time we ask, of course, we get it from the resolver cache. And then, only then, we establish a TCP connection, which is step 9. 9 steps to get to the connection part, right? And Node is going to do the same exact thing. By just you specifying http example.com, this is happening behind the scenes. Here's a DNS packet, just for your information. Here's a source if you want to take a look at what is it and how does it look like. The most important thing for me here, if you ever want to understand, this is the DNS header. Right? This is just the IP header. This is the UDP, because there's a destination port, destination source port, source address, IP address, destination IP address, and this is like just the IP protocol. But this is the most important one, transaction ID, or sometimes called query ID, right? The transaction ID, because the DNS is not really it's a message-based protocol, and it's not really a request response system, right? It's not like I send a request. It's not like I send a request and I'm supposed to get a response. No, it's just a message-based system. So you can send 10 messages and never expect anything back, right? It's a message-based. So we need some communication that we can add on top of UDP, right? What is it? I said UDP or DNS? UDP is not a request response, yes. So the transaction ID is an identifier that you create as a client, and in the client here I mean the resolver, and you add it to the DNS packet, and you say, hey, I'm sending you a UDP request message. Here's my query ID, and you put the transaction ID there. Boom. So when someone responds back to you with the answer, they put the transaction ID in their message. So you link them. Oh, this queries belong to this. This way you can send 10 different queries at the same time. And when you get back, you know that, oh, this belongs to this, this belongs to this, this belongs to this. Unlike HTTP doesn't have that. If HTTP had a request ID baked into it, we would be able to send multiple requests at the same time without forcing them to be in order, right? And that's why we always have to send it on the same connection, on one connection, and we have to wait for the response for that request to be sent, because otherwise we don't have this correlation. Unless you want to build something on top of it at the application layer to have this link that this request is belong to this response, then you can do it. And you might say, Hussein, I do this all the time. I send a request and I get a response. How does Node know? Well, Node doesn't. You sent a request, and Node creates a TCP connection just for this request, and it only sends one request. So if it receives a response on this connection, it means that, oh, this response must belong to this request, and it just sends you back that message saying, yeah, here you go. Here's some notes about DNS. There are many layers because we want redundancy. right? And that's where the beauty of this, right? If you look at this diagram, there's a lot of layers, and there are many authoritative name servers. So if one is down, then that's fine. I can have another one, and the TLD will know about it because there is health checks going on left and right to check if the authoritative server is down or up. Okay? And there's root servers, and then there's a lot of layers. So it's like it's spread, right? A .com server asking for google.com might give me a different authoritative name server than HusseinNasser.com. That's a different authoritative name server, right? And then we get this the different ANS, and it's just like we're spreading, right? So the load is not is distributed, not on one machine with billions of rows, right? And even there is a lot of mechanisms to search through that. And even there's algorithms for indexing. Of course, there's a lot of stuff going on here. It's not like we're doing full table scans here. We need to also be efficient. Yeah. And of course, DNS doesn't mean also just going this resolving, right? You can have host file. And boy, I cannot count how many times I use this host file, right, for networking. You probably used it yourself, right? A host file is a hard-coded instance on your operating system that tells you, hey, I want you to ignore the DNS and always map this entry to this IP. This is what the host file is. So if I ask you example.com, look up in this file first before you do the DNS. If you find it, use that. So I use it all the time to block something or change the traffic. Let's say if a database server, we're using a server called DB1, right? And let's say DB1 as a database is destroyed. We just moved it, and now it's DB7. And now imagine all the thousands of applications using DB1, right? In their configurations. What I do, I go to the host file and change. I get the IP address of DB7 and literally say, hey, DB1 is now this IP address. And now everything just magically works, right? And that's things I've been doing for like years and years, right? This is one example of you can do it, right? So host file is very, very useful for the administrator. Yes, so host files. So you can see that DNS is not just about sending UDP queries. They can also be I/O, file I/O. And do you know what file I/O are? They are blocking. Yes, they are synchronous and blocking, right? Unless you do it. And that is one of the main reasons why libuv or DNS is being done on its own thread, because of this, right? Because we're using literally what you're using an internal kernel function, get address info, that does both, right? Does this and this, right? It's just like, hey, do your thing. And it's a lot of people criticize this function, but hey, that's all we have, right? So DNS is also not encrypted by default, which is it's a topic of heat and contention. People like it to be not encrypted and port 53 so they can look at their queries, and some countries use it to block website that you're not supposed to see based on their ideology, right? Hey, I don't want you to looking at this website. And DNS is easy to block, right? It's like, hey, it's a clear text, so I can know what website you were visiting. And there was like a lot of attacks against DNS hijacking and DNS poisoning. I don't want to go through this. I talked about this in my course, network course, if you're interested. But attempt to solve this are DOT and DOH, and God, still people prefer one over the other. It's just so complex to set up that, in my opinion, I don't think it's ready to be deployed in the public. I think it's being deployed, but it's just DOH is basically DNS over HTTPS. DOT is DNS over TLS, which the network guy prefer this because they want to know their DNS traffic. They know today by using port 53. DOH will use it on top of HTTPS. And if you use it on top of HTTPS, that's 443. I have no idea if this is a HTTP query versus an actual DNS query. And they don't like that because they funnel the network and filter it such that if it's DNS query, I want to send it through this switch. If it's an HTTP, I want to send it through this switch. They want to do this. And I kind of understand that they lost that with DOH. So people, and it's easy to block DOH because eventually to do DOH, you have to do what? I forgot. You have to connect to a specific well-designed, well-known HTTPS provider that supports DNS, the DOH. And if you know these and block them, then you basically can block DOH. So even that doesn't stop ISPs from like blocking DOH, right? So yeah, it's a whole thing with this DOH, and I lost hope following all what's going on there. It's a mess, you guys. It's a mess. This stuff. But yeah, what we're interested in here is just the technology aspect of it. All right. So let's go to the DNS in Node. Well, in Node, we're using the thread pool. And this is done with libuv, actually right here, right? The DNS is being done on the thread pool. And the reason we're doing it because you're using this function that's called get address info, which reads both locations. It reads our host file. If it's not there, then it does the resolving, right? On the network, doing everything that I talked about. And so why though? Why not just do? Because that's the question, right? If DNS is just UDP, then it will be just normal network IO, which is completely asynchronous in Node, right? But no, we cannot do it because we need to look at the host file, which is a file IO. And how do we do file IO? Well, to do a file IO, we have to do the thread, right? So we're stuck. That's why we have to do DNS on top of file IO, on top of the thread pool. Right? That's just basically the gist of it. So yeah, it's a mixed workload, and it's blocking. Yeah, we'll go through an example. But by default, if you do that, the DNS resolving, the default DNS resolver, and I think you can override that. This does this, which does a thread pool. So even just a normal request like that, we have to do DNS before that. Even if things are cached, we have to do DNS. So we do a DNS and we find the IP address. And then when we find the IP address, we can connect, because that's what the purpose of a request is, to connect and then send our GET request, right? So what's happening here is like the DNS query is happening on one of these puppies, on one of these threads. So too many, I don't know English. Too many DNS queries may starve your thread pool, this net. So be careful. Abunai. So you guys, we talked about this. So there are two types of DNS resolution, right? So there's the DNS type, the normal one that uses get address info, and it uses the thread pool, one of the threads, and that thread is being blocked to do the DNS while the main thread is happy and shiny and doing asynchronous stuff. But then you can opt to, of course, we talked about this. We'll read the cache first and then do it on network, right? So that's what we call the resolve. To do a DNS, So that's what we call the DNS lookup. So the DNS lookup, which is the default, reads the file, the host file. If it's not there, it does a network. Okay? But then there is something called resolve. DNS resolve only goes to the network, and it never checks the host file, right? And if as a result, it is asynchronous, and it is using this part of things, not this, right? It uses the network IO. It's just like another UDP. It becomes just the normal UDP stuff, right? It uses that. So that's another thing we can discuss, right? So let's talk about this. Example, implicit DNS lookup. So this, I'm requesting a Node.js here, an HTTP. I'm sending a request, and I'm doing an HTTP example.com. This is actually doing a file IO. It looks up my example.com inside my host file. If it's not there, it just goes and through the network and ask my router or ask my resolver, or like, where's my IP address for example.com. It goes through the root, it goes to the TLD, it goes through the authoritative node server, and maybe the resolver has a cache, so it just responds immediately. So that is completely indeterminate. You have no clue whether it's going to be fast or slow, right? And even locally, it's being cached. The DNS is being cached for a given amount of time, and that time is controlled by the DNS resolver, UDP message. And we send, of course, the request to end the stream, and then that's it, right? So that's an implicit DNS lookup that you don't feel, but it's there. So before we even establish the TCP request, there is a DNS query going on. And just watch out for that. May or may not. Yeah? Because maybe it's cached. And here is an explicit DNS lookup. Again, lookup. If you do a lookup, this looks through the host file, and then it goes to the network. And it's using the libuv to do that, right? This is an explicit lookup. So if you do that, you can do DNS, and we get all this beautiful stuff: the error, the address, the family, which is IPv4, whatever, right? And it will tell you, hey, we're going to run it through this example in a minute. And here's an example of a DNS resolve, which is that I'm using the library of DNS, which we required here also, right? But I am resolving for, I believe it stands for IPv4. So resolve IPv4 addresses. This is always go network, right? It's just another ePOL concept with the Linux, at least. Right? So we're sending that and says, hey, do a DNS. Give that to me. Here's some server bind gotchas, you guys. Have you ever seen this before? If you pass in a string, I think we talked about this a little bit. There is a difference between doing server.listen with just a port and doing server.listen with an actual name. This binds immediately because it tells Node to listen, and subsequently the kernel, to listen, to create a socket and bind it to all IP addresses that you can find. However, if you specify what IP address, what host to actually do the lookup, sometimes we need to do DNS, especially for local host. I need to find your IP address for local host. What do you mean? Right? Because you might need 127.0.0.1. Because that in itself, even localhost is a DNS lookup. You might say, what? Localhost is just 127.0.0.1. No, it could be : 1. So that's in itself a query to the host file. And that's the default. It says, all right, localhost is actually this IP and also this IP, and also it can be whatever you want, right? And you can have your own host name here. That means anything. So just watch out for this initial phase. It's interesting. Something gotcha. We're gonna do this. All right. We talked about DNS. We talked the difference between lookup and resolve. Right. Lookup is lookup this host. It's a blocking call. So we do it in the thread pool and the libuv, while resolve is done on the network directly. Just it never touches the files. Just go to the network, always through UDP, normal polling operations. So we talked about Node DNS, and yeah, how about we do these guys? There's some examples. Let's go. All right, so we're gonna do strace -t. I want the timestamps. dash F, I want the forks. And I want DNS. DNS is 17. Then 70. We're gonna show you what it does first, huh? Might be a good idea. I'm doing a request to example.com, and I'm just printing. I'm not even printing the response. I don't care. I just send that, and that's it. So I want to see if we happen to make that DNS call. I never talked to example.com before on this machine, so we'll take a look and see if this will work. And we need, of course, to call node. And I have this another control open because I might need to do TCP dump, but we'll find out. Maybe we don't. There you go. Did we? I should have printed it to a file, huh? Not only we did, look at that. Get address info has been called. And we got the example.com, you guys. It looks like we're using this DNS server. This is my local DNS server. And we established, there you go. That's the first DNS request. Sock datagram is the DNS request. So you can see that we're connecting to this IP address, which is my DNS server, 127.0.0.50, because I have a MDNS configured on this. Might be a bad example because it's a little bit complicated. But assume this is my DNS server resolver, right? So node, before it actually send all this mumbo jumbo to example.com, did connect to this IP using UDP, and it started sending a bunch of stuff as sending messages, see? And then I'm gonna scroll down to when we got responses. And look at the responses we got. We got these responses. These are we got 192.168.7.9, which is my machine that I'm connected to. But then we got, look, that's the IP address of example.com. Remember when we did the NS lookup? We got a bunch of them, and it's, to me, I think it's a bug because we're trying to connect to all of them unnecessarily, might I add. Because look, it's doing a bunch of connections to these. Right? AFNet, that's the TCP connections, connecting to all of them, unnecessary. Right? And then there's a bunch of IPv6 too that came back and says, oh, network unreachable. And maybe all of this happening in the thread pool, because like which IP, which process? This is 45, right? So let's just keep that in mind. All of these happen in the 45 thread. Like we're connecting to every possible IP address that we got, even the IPv6 ones. Then we get errors, then we get this, then we get that. We did an epoll to find out the results. And there's a bunch of configuration, TCP no delay, that's the Nigel algorithm. And then I'm interested in the actual TCP request that we sent, right? Here you go. We actually sent a request. This is the response. We got back the response from the socket. But this is the right. This is the connection because we created the socket over here, I suppose. Yeah, that's the connection. That's the IP address we picked up eventually, and then we connected to it, and then we added. We did this in the prol phase, not the prol phase, the prepare phase. Then we sent something. We wrote something here. We write. Did we write something? I can't remember. Yes, we did because we sent the request, right? So we have to wrote something. Then, of course, somewhere here, this is the request. We send the request, get http/example.com. And then scroll a little bit down, we got the response. But look at which thread did that happen in. 38, right? It's a different thread than the DNS thread, which is 45. I love this stuff, you guys. I love it. There's so much stuff here, you guys. There's so much, right? And again, we can go through all of this. We can play with some examples. Like here's a DNS lookup. I'm not going to go through details on all of them. I think that just this proves that, just one example, that it's a proof that we can play with that stuff. But this is a DNS lookup. You use the lookup functions if you want explicitly do DNS, let's say, and you want to instead connect directly. You want to control the DNS. And this is a resolve, which always uses the network. That an example of where we're binding, but if you notice, I'll try to do this. Let's do this actually. Right? I'll run this, and we're binding in 8080. And let's run it here. This is creating a server and binding on 8080. And then we're looping. I'm going to make a intentionally very large loop just to prove that this takes time. I think we did this example at some point, right? 173, listen. Like here, the connection already happened. I mean, the binding already happened. Although the initial phase didn't finish, this server is ready. So if I do telnet 127.0.0.1.80.80, see, I can connect, right? Because the servers is already, even though we didn't finish, even though we didn't start with the event loop. So if I kill this and I do the other one, which is only listening on 8080 localhost, and I try to connect, oh, too slow. Let's do it again. I do that, and I try to connect. It fails. Right? Let's kill it again. I try, fails. Try, fails. Try, fails. Try, fails. Try, fails. Now try again. I wonder which IP did we pick. Let's try again. So it's 127 failed. That means it's listening on the other IP. That, and I'm gonna do localhost. Fails. Localhost. Fails. Localhost. Fails. Now localhost succeeds. Right? So this means that we didn't actually listen on 127. It really depends on what the DNS came back with localhost. That's why you have to be careful, because localhost does not mean 127.0.0.1. It means whatever localhost happened to resolve to, right? And this is basically what it was. All right, let's cut this lecture short, and I'm gonna see you in the next one. You take care, guys. Hope you like this stuff. I hope you enjoy this deep dives, because I do. There's so much to explore here. It's just like so little time.